Okay, and we have been discussing about radiation for the past 2 classes, right? And can anyone brief what we have done till now in radiation?
Some we learned radiation shields and re-radiating surfaces.
1 minute, I'll come back. I'm sorry. Right, you are able to hear me, right?
Yes, ma'am.
Okay. Can you please brief what we have done in the previous classes?
We learnt about Planck's distribution law,
Mm,
then Wien's formula. Then we went to discuss on fractional emissive power. Then we
mm,
saw about non-black surfaces, their emissivity, and we saw the parameters affecting the radiation for real surfaces. Then we saw how radiation is exchanged between surfaces. So there we introduced shape factor to deal with double integrals.
mm,
Then we saw reciprocated theorem. Uh, for the first class, then second class we discussed about the um, heat rate transfer for black body, real surfaces. Then radiation exchange between black body. Then we discussed radiation exchange between real surfaces. Under that, we discussed a few cases for two small gray bodies, then two long parallel plates, then between small gray bodies inside a large enclosure, and then two concentric cylinders and spheres. And after
mm.
that, we discussed about re-radiating walls and radiation shields.
Okay. Okay. Now, the only topic which is left out is when there is a participating medium present in between the radiation surfaces which are exchanging the radiation, right? So the examples for participating mediums are CO2 and H2O. And when we have air and nitrogen, it will not participate in radiation transfer, right? So the CO2, CO, H2 and all will be there in a combustion chamber. So definitely that will try to intervene the radiation heat transfer. When we have such cases, how to calculate the radiation exchange, especially the emissivity of your gaseous mixture, we should know. That we'll now discuss. And now I am trying to move to the whiteboard. Now the whiteboard visible?
Yes, ma'am.
Okay. Okay. So when we consider the intensity of radiation, that will decrease with the distance or passage it passes through when you have gaseous mixture, right? And let I lambda be the intensity of radiation which passes through a thin layer of gaseous layer of thickness dx, then it will get attenuated to an amount of di suffix lambda, right? Attenuated to an amount of di suffix lambda. So this amount which is attenuated is directly proportional to this distance and also the initial intensity of radiation, or this can be written as the decrease in intensity of radiation is equal to the proportionality constant being replaced by attenuation coefficient multiplied by I suffix lambda into dx, and we try to rearrange the terms. This is I suffix lambda naught to I suffix lambda x. This is lambda. So you will get I suffix lambda x is equal to I lambda naught into exponent of minus a into a suffix into x, right? So this will again be replaced, this x. What is x? That is the distance through which the intensity of radiation travels in a gaseous phase and a gaseous mixture, right? So if you want to represent for the whole enclosure where the gaseous mixture is available, so this x is being replaced by mean beam length. So now the x is being replaced by L suffix 12, where this L suffix 12 is mean beam length, and this is generally calculated using the equation 3.56 3.6 into volume of the enclosure divided by the area of the enclosure, or the volume occupied by the gas divided by the area from where the radiation is emitted. All right. So now we are interested in knowing the emissivities. Emissivity of the gaseous mixture. Right. Gaseous mixture and also absorptivity of your gaseous mixture. So generally this emissivity is going to be a function of your, this is gas to surface, partial pressure at which your gaseous mixture is available or existing, total pressure of your gaseous mixture, concentration of the gaseous mixture, and also your temperature of the gas. Whereas the absorptivity of the gas is generally gas to the surface, generally is a function of all these parameters: partial pressure, total pressure, concentration, and gas temperature, and also the surface temperature. So this you have to remember when you try to do your calculations. Now how to get your emissivities of your gaseous mixture, right? So can you just refer your data book? I'll tell you the page numbers. Absorptivity of CO2, and I've also already told you the participating mediums are H2O and CO2. So we are interested in knowing the emissivities of the gaseous mixture, which consists of H2O and CO2. Can anyone tell me the page number? Yeah, page number 105. Data book. Please refer page number 105. What is written? So emissivity of CO2 in a mixture at 1 atmosphere, right? And if you see page number 107, so emissivity of H2O at 1 atmosphere. So for both the things, your x-axis is temperature in Kelvin, right? What are the different lines corresponds to? Yes, you are not opening the data book which is loaded there.
Pressure, ma'am, that lines.
It is not only pressure. It is pressure, partial pressure of CO2 multiplied by your mean beam length, right? Is it not? Page number 105. Partial pressure of CO2 multiplied by this mean beam length value is corresponding to the different lines in your chart, right? So you know the partial pressure of CO2 and you know how to calculate your mean beam length, and you know the temperature at which it is existing. Accordingly, you will be able to calculate your emissivity of CO2 and emissivity of H2O using the charts available in page number 105 and 107. So the emissivity of gaseous mixture in this case is going to be emissivity of CO2 plus emissivity of H2O. So this formula is applicable as long as your gaseous mixture is existing at 1 atmosphere. What if it is not existing at 1 atmosphere, right? So other than 1 atmosphere. If the total pressure is other than 1 atmosphere, we use this expression with the correction factor for CO2 multiplied by emissivity of CO2 plus correction factor H2O multiplied by emissivity of H2O minus the overlapping between these two gases, right? And you know how to calculate this emissivity of CO2 similar to this, and emissivity of H2O similar to this. Now we'll see how to get this correction factor for CO2, right? So the correction factor for CO2 is available in page number 105, sorry, 106. Can you just see page number 106? So in which the chart you have is x-axis is your total pressure in atmosphere and y-axis is your correction factor, and different lines corresponds to your partial pressure of CO2 multiplied by your mean beam length, right? So many atmospheres meter. So for different lines you can get your CO2. The same thing is applicable for getting your correction factor for H2O, right? And this is in page number probably 108. Yes, 108. Page number 108. And you have to subtract the overlapping quantity by using this term, which is available in page number 109. Are you able to see these page numbers? Please someone tell me.
Yes, ma'am.
Okay, page number 109, what is there?
Inverted parabola for the Delhi.
Daily, right? So what is your x-axis in this?
The partial pressure of H2O.
Partial pressure of H2O divided by partial pressure of H2O plus partial pressure of CO2, and your y-axis is your delta E, and these different lines corresponds to different PCO2 plus LMS plus PH2O into LMS, right? And if you see, there are three different charts, right, in page number 109. So these three charts are for different temperatures of the gaseous mixture. Please try to remember the temperatures given here are for gaseous mixture, right? And in case if you are asked to get delta T, you are supposed to get your delta effectiveness for 1000 Kelvin. What will you do? It is not available, right? You can get it for 811 and you can get it for 1200, but it is not available at 1000 Kelvin. What will you do?
Should we find out what it is in both 811, 1200 and extrapolate to find 1000?
Okay, please extrapolate by assuming that this delta effectiveness is varying with respect to temperature linearly, right? Okay, now you know how to calculate your gaseous temperature, emissivity of your gaseous mixture, right? Okay, now maybe what, how will you write the general equation now? Q in this case, right? What are the two values now?
Two values for no?
Gaseous temperature and surface temperature, right? It is enclosed. The gaseous mixture is enclosed in a, most of the time it is furnace. Furnace wall temperature, the other one, right? Okay. Next is absorptivity of gaseous mixture. So now we'll see how to calculate the absorptivity of gaseous mixture. So you will be using the same chart here again, but with a different values for your y-axis and your different lines. So this absorptivity is absorptivity of CO2 plus absorptivity of H2O minus difference in absorptivity, right? And so this absorptivity is equal to, sorry, this is effectiveness. You know how to calculate this effectiveness, sorry, emissivity, right? How will you get delta epsilon? Using the chart, right? What was the temperature you have referred there? At what temperature you have referred? There were two charts, right? That was the gas for gas temperature, right? But now you have to calculate this delta emissivity, but at the surface temperature or wall temperature. At surface or wall temperature, right? So now what is your absorptivity of CO2? How will you calculate your absorptivity of CO2, which is emissivity dash of CO2? You know how to calculate this emissivity dash of CO2, emissivity of CO2, right? And I'll tell you how you can go about it, and multiplied by T gas divided by T surface or T wall to the power 0.65 multiplied by your same correction factor. Similarly, H2O you can write it. Now we will see how to get this emissivity dash from the same chart which we have used for calculating your emissivity of CO2, but the y-axis must be temperature of your wall, and the different lines corresponds to partial pressure of CO2 into multiplied by your mean beam length was the previous value which we have used, but this time this you have to multiply it with your T wall divided by Tg. Right, that's why we have seen, no, the absorptivity is going to be a function of T wall again. Now, is it clear for you? Is it clear for you?
Ma'am, can you explain E dash CO2 again?
So you know how to calculate your this emissivity of CO2, right? That is clear to you?
Yes, ma'am.
So in which you had emissivity here, temperature of the gas here, different lines corresponding to, if it is CO2, it is CO2, partial pressure of CO2 into LMS, this mean beam length. Now they also say this is gas to surface, LGS, both are same, right? This is how you calculated your emissivity, right? Varsha?
Yes, ma'am. Yes, ma'am.
Okay, now in order to calculate your emissivity dash, instead of your Tg, you take your wall temperature here, right? You have to take the wall temperature given in your problem to refer your x-axis value, and for different lines, for the value you have to calculate is PCO2 LGS multiplied by T wall divided by T gas. But the values are same, right? Only thing you have to take this multiplication factor Tg by Tg, and accordingly you should look for the line corresponding to that, right? So that will be your E dash. Is it clear?
Okay, ma'am.
Same way for your H2O, and same way, I think correction factor, they have not said anything. Let us not get confused. If I come to know about correction factor for absorptivity, I'll let you know, right? So now the Q is equal to Q by Q is equal to Q by A is equal to, right, your emissivity of gaseous mixture into temperature of your gaseous mixture. This why they have given it as, this is, maybe I am not giving it right now. I'll erase it. Into sigma Tg power 4 minus alpha G sigma T wall power 4. This is the equation which you are supposed to use when you have a participating medium in your, sorry, this is again, when you have your participating medium in your furnace, right? Is it clear? Okay. So in these things, we never had the surfaces which are true, which are real surfaces, right? Furnace surfaces were considered to be black in this case. What will happen if you have surfaces or wall which is non-black? How will you do that? So for this we have a expression, Hotel's, this is T and T, Hotel's formula. Which says that Q of gray divided by Q of black. So this Q of black is nothing but this is equal to emissivity of the wall, this is wall, divided by 1 plus, and this is applicable as long as your emissivity of wall is greater than 0.8. So with this, for radiation theory part is over, right? I think you have got too many equations for this participating medium. Let me summarize once again. So emissivity of the gaseous mixture is the emissivity of individual gas, summation of emissivity of individual gases like CO2 and H2O as long as the gaseous mixture is existing at 1 atmosphere. So if the gaseous mixture is existing at a pressure other than 1 atmosphere, we need to include the correction factor CCO2 and CH2O, and both these emissivities and also the correction factors are available in the form of charts in the data book. And when you have the mixtures, we always try to remember to subtract the overlapping factor, which is delta emissivity, which is also available in the form of chart, and this can be done. So next is and when you have your emissivity, you know how to calculate it, and absorptivity, again we have used the similar equation for absorptivity, but only thing is you will be again referring the emissivity charts itself, but with different x-axis value, that is wall temperature, and different values on your lines corresponding to partial pressure of the component multiplied by LMS multiplied by T wall divided by T gas. That is the thing, right? Now shall we do one problem on this so that, and one more thing, when you want to see, this is as long as this equation, is applicable as long as your furnace wall is perfect black surface. In case if you have a perfect, non-black surface, then you have to use this Hotel's formula, no other way of doing it. So this is again applicable. You know how to calculate this Q black using the earlier equation, that you have to multiplied by your emissivity of wall plus 1 divided by 2, and this is also applicable as long as your emissivity of wall is greater than 0.8. Let me give one problem so that you will try to refer this charts, and if you have any doubts you can get it clarified. I'll only be dictating the problem now, right? Can you take it?
Yes, ma'am.
Yes.
Okay, cylindrical furnace of 20 centimeters diameter and 20 centimeters height, sorry, 20 centimeters height is maintained at a temperature of 650 degrees centigrade over its entire volume. Let me repeat the sentence. A cylindrical furnace of 20 centimeters diameter and 20 centimeters height is maintained at a temperature of 650 degrees centigrade over its entire volume. The next line is the total pressure of the combustion gases is 1 atmosphere. The total pressure of the combustion gases is 1 atmosphere, and the mixture contains 11% CO2, 11% CO2 and 0.5% H2O by volume. 10.5% H2O by volume. Calculate the emissivity of the gas volume. Calculate the emissivity of the gas volume. The answer is 0.106. You can now refer your charts and just check.
Ma'am. Ma'am.
Yes, who is that?
Ma'am, Madhu, ma'am. Ma'am, the
Mm,
water
yeah.
volume is 10.5%, right? Or 0.5?
Uh, 10.5, yes, pa.
Okay, okay, ma'am.
Ma'am, for this question, 650
Yeah.
degrees Celsius, from 650 degrees Celsius is the temperature of the gas.
You want to know the problem again, right?
No, ma'am, I'm asking if 650 degrees Celsius is the temperature of the gas.
1 minute. Yes. Maintained at 650 degrees over its entire volume. That means gaseous temperature, right? 650 degrees is maintained over the entire volume. What is emissivity of CO2? So 650 is in degree centigrade. You have to convert it into Kelvin, right? Because the y-axis is in Kelvin. Varsha?
Yes, ma'am, I converted. It's 923 Kelvin, and the emissivity of carbon would be around 0.2.
Okay, what is your what is LMS? Mean beam
I
length?
got 0.18.
Huh?
0.18 meters.
3.6 times volume divided by area.
Yes, ma'am.
How much you got?
0.18 meters.
18 meters. Others, is it fine? So multiplied by your partial pressure of CO2. What is the partial pressure of CO2? It is 0.11, right?
Partial pressure is 0.5.
It is 11%, right?
Yes, ma'am.
0.11
11%.
into. Yeah, yes. Yes, ma'am.
11% by volume. So I did mole fraction into total pressure.
Okay, then how much it comes?
I got partial pressure as 0.511.
0.511. Can't you take the pressure fraction as a mole fraction? You can't take it? Okay, let us check the final answer. 0.55 into 0.18. Right? So what is your emissivity of CO2?
I got 0.2. Close to 0.2.
0.2. Okay, emissivity of H2O.
I'm doing that now. 1 second.
Okay, please do.
Ma'am,
Yes.
as you said, like if we take is 0.11 as partial pressure and 0.105 as partial pressure, we are getting the answer, ma'am.
Okay, I think you can, Varsha, you can equate this. You have done this kind of thing in your process calculation, right?
Yes, ma'am.
Volume percentage equal to pressure fraction, partial pressure fraction. What law is that?
Ma'am, Dalton's law of partial pressure.
Okay, now, so based on that, what is your, who is that?
Ma'am, Sudarshan.
Sudarshan, what is your emissivity of CO2?
Ma'am, 0.068. I got
67. Yes, ma'am.
0.68. Yeah. What?
And emissivity of H2O?
0.038.
0.038. Then?
Adding directly, you get the total.
Okay, emissivity of gaseous mixture is 0.068 plus
0.038. Yeah. 0.104.
0.10. Okay. Now shall I dictate one more problem? Okay, please let me know whether you want to have list of problems for radiation or you don't want.
We want.
But you keep complaining that I keep giving you assignment and you always come and ask for extending the line date. Huh? Pardon?
Can we try to do it on our own, and can we discuss it in class after that? Because whatever doubts we have while solving the problems, like most of us have the doubts, so we're not able to clear it out on our own.
Yes, ma'am.
Okay, I'll be giving you the list of problems, posting you list of the problems. And I also know what will happen in that case, right? Only one or two will work out, and even without working out, they'll just come and ask for doubts. Will it not happen?
That might happen. Can we? Okay, ma'am, we'll all submit whatever we've done, we're able to do. And in case we have doubts, can we ask it in the next following class?
Okay, if you have, see, I am not fixing you any, see, closing time is there, but even after that, you will be able to you will be allowed to submit. That option I will fix.
Okay.
Right?
Okay, ma'am.
And if you have any doubts, you can post it in chat. I don't want you to hold it till we meet next time. Whenever you do, you just keep posting it, and whenever I see and whenever I have time, I'll keep responding to that answer to the thing, right? Is it fine?
Yes, ma'am.
So that then and then it will get cleared.
Yes, ma'am.
And in case if I get delayed in reply, please wait till I reply. Don't mistake me, since weekend Deepali, right?
Yes, ma'am.
Okay, but I'll try to post the list of problems at least by tomorrow evening. Most probably by tonight or by tomorrow evening I'll post it. You keep working out, right? So as per the classes are concerned, I feel that this is going to be the last class. Okay. This is going to be our last class and I have completed all the theory part. Okay. Varsha, you are not responding.
Yes, ma'am. Sorry, ma'am. It's raining here, so my internet is slightly weak.
My internet or yours?
Mine, ma'am. Mine.
Okay. So we are not meeting tomorrow.
Okay, ma'am.
If some other faculty wish to take my classes, they can take it. You can inform them. I think Muthukumar sir wanted to handle one class. You can inform Muthukumar sir.
Okay,
If
ma'am.
he is free, let him handle it, right?
Okay.
Okay, thank you for all your cooperation. And we'll give you the list of problems and we'll finish it up. Anything else you want to discuss?
No, ma'am. I think that is it.
Okay, thank you. If anything is required, please keep posting it in chat. I'll reply. Thank you.
Yes.
Bye.
Thank you.
Thank
1
you, ma'am.
minute, I'll just take the attendance. I think till now we had 32 classes.
Does anyone have a shortage in attendance?
I informed you, right?
That we've done. Other than that, nobody else.
Now you know, no? These three classes.
Yes, ma'am.
Based on that, you just identify whether those three are have attended or not. Find out from them.
Okay, I will, ma'am.
You just add those three classes and calculate it for 32, 32 and find out whether they are missing it or not.
Okay, okay, I'll do that, ma'am.
I need some time to calculate it because this has to be converted and done. Once that is done, I'll let you know.
Okay, ma'am. I'll also try. I'll doing it myself.
Okay. And today one more session is there, right? For presentations, Varsha.
Yes, ma'am. Last one.
Yes, ma'am. Yes, ma'am. The last.
At what time they'll come?